Like all great scientific theories, quantum physics was developed to explain a number of phenomena that could not be satisfactorily explained by existing ideas. In the case of quantum mechanics, the existing theory was classical physics, with deterministic macro-scale ideas like Newton's laws of motion. The new physics, quantum mechanics, did not suddenly appear fully formed, but rather developed as a series of adoptions and adaptations of these classical ideas. As quantum theories were being created, some of the leaders of the quantum movement shared their thoughts with the world and one another. Every feature of the electromagnetic theory, however small, is duly recognized and receives its counterpart in the new conceptions. Bohr, 1924. Many of the features of the classical theory to which it owes its attractiveness can be taken over, unchanged, into the quantum theory. Dirac, 1927. It must be demanded that, for the limiting cases of large masses in orbits of large dimensions, the new mechanics passes over into the classical mechanics. Born, 1933. And with this correspondence principle, we can introduce the correspondence principle. The correspondence principle isn't really one thing, and we will go through a couple of the specific definitions of it, but the thing that they have in common is that there is some sort of congruency, coherence, or, correspondence between quantum and classical physics. For someone like Bohr, who imagined a number of classical stationary states being related in a quantum way in his model of the hydrogen atom, this correspondence meant that classical mechanics was a literal and fundamental part of quantum mechanics. As the field developed, correspondence became more of a mathematical analogy than a visual understanding. An electron was not literally rotating about the nucleus, but it could be understood using mathematical tools borrowed from classical physics like the rigid rotator model. Eventually, correspondence began to take on the meaning that classical physics can be recovered from quantum models, specifically at high quantum numbers, reaching what is called the classical limit. This idea has also been extended in a more philosophical way to yield the general correspondence principle, which says that a new full theory should be able to predict and explain everything that the old one could in order to be valid. Thus, under this idea of the correspondence principle, one could describe classical physics as essentially a very efficient approximation method for quantum mechanics in some circumstances. There are yet more definitions of the correspondence principles, and we will get to a couple later on, but for now the main definition for this video will be that at certain scales or limits, quantum physics becomes classical physics, or at least the parts of it that could be explained without reference to quantum theories. Stuff like superpositions, entanglement, and tunneling disappear, or become so insignificant that it looks like they did. All operators commute. The only uncertain state is the one you're in before you find the right equation to plug your numbers into, and we are left with the deterministic world that we all know and love. Kind of, not really, but mostly. Let's get into it. Part 1. The classical limits. Perhaps the clearest, mathematically clearest at least, example of the correspondence principle is in the idea of reaching the classical limit at large quantum numbers. In the way we learned, this can be understood as quantum physics becoming classical physics when the quantum numbers, so the energies, are large enough. For example, as we increase the quantum number of a particle in a box, we approach the sort of uniform distribution that we would expect in a classical system. Of course, we still have this sinusoidal behavior, but that will become unimportant as n approaches infinity and the fluctuations average out at a local level anyway. As Macquarie 318 so sagely invites us to consider, as we increase n to infinity, a particle in a box matches the standard deviation and expected value of a uniform distribution. Bohr also found that as n increases, a hydrogen atom spectrum starts to look more and more like the classically calculated result. It's important to note here that n represents any quantum number, not just n. For a quantum harmonic oscillator, increasing the quantum number causes the probability density to match that of a classical harmonic oscillator, as shown in the Python output here, which includes the wave function at n equals 25, and a corresponding classical probability density. The density does not look all that similar, but it does match as a local average, as you can see here, just as in the particle in a box case we saw earlier. The idea that we reach the classical limit at quantum numbers as quantum numbers get big is commonly stated, but it is not actually true in all cases. As a 1984 paper from Richard L. Lipoff points out, both the rigid rotor and a particle in a 3D box fail to reproduce classical behavior at the n goes to infinity limit in terms of what is called frequency correspondence. This means that the frequencies of transitions between various states, even at high n, are not the same as they would be in a classical system. They remain quantized, with each successive transition being h over the moment of inertia above the previous in these two examples. They still retain what is called form correspondence, however, which means that the frequencies follow the same functional form as equations, but the actual transitions do not densely cover the curve those equations define. Leibov argues that form correspondence is less physically relevant because what we end up observing is the transitions, and those remain quantized by non-reducing difference. What makes the quantum harmonic oscillator different? As we know, it only has one transition frequency that does match the classically expected one, regardless of what n is. Thus, it seems that the n goes to infinity classical limit cannot fully get us to the correspondence principle. So is all hope lost? Is there no relatively straightforward mathematical way to reduce quantum physics to classical physics, besides hand-waving and rough approximations? Not quite. Planck's correspondence principle uses another limit to achieve correspondence, which is best summarized with the following equation from the Leibov paper. The limit as h goes to 0 of quantum physics is equal to classical physics, where h is, of course, Planck's constant. Max Planck applied this limit to his law for the radiation of black bodies to yield the classical Rayleigh-Jean. Hold on. The limit as h, Planck's constant, goes to 0. Constants don't go to anything. That's what makes them constants, right? Sure, it's a small number, but it is a number. That would be like taking the limit as pi goes to 0. That would be nonsensical. Or would it? What is the area of a point? 0, right? That's what classical geometry tells us. However, when we zoom in close enough, we see that the point is actually a circle, with area pi r squared. We do want to recognize this fact in what we can call quantum geometry, while being able to recognize that a point has an area of 0 at the classical level. We could say that the radius is so small that it approaches 0 at classical scales, which may make sense, but that complicates using radii at larger scales. Or, we could imagine that the quantum geometrical constant pi goes to 0 at the classical level, which gets us the same result. It's a similar idea here. Okay, as I was saying before I was so rudely interrupted, if we apply this limit to Planck's law for blackbody radiation, we get the classical Rayleigh-Jean's law. This limit can also be used in the previously discussed cases of the particle in a 3D box and the rigid rotor to achieve frequency correspondence. When h goes to 0, the frequencies are no longer quantized, and we get a classical answer. When using this limit, we can also turn the Schrödinger equation into its classical analog, and in fact, the limit h goes to 0 can be said to define classical physics. Part 2. Mathematical correspondence. There are a couple other important examples of the correspondence principle at work that I want to point out. The Ehrenfest theorem, for example, states that the time derivative of the average position is equal to the average momentum over the mass, and that the time derivative of the average momentum is equal to the average value of the negative of the derivative of the potential energy as a function of position, with respect to position. This might look like a bunch of whatever, but this is actually the quantum analog of Newton's second law, as I will show in this movie. Okay, so this is Ehrenfest's theorem. The first bit is just saying the time derivative of position, so velocity, is equal to momentum over mass. Rearranging a little bit and plugging in the average values for the actual values, we can get momentum is equal to mass times velocity, which is just the definition of linear momentum. This reflects how in classical systems, which are often essentially large ensembles of many probabilistic systems, the average value ends up being the only value. Now for the second part. The statement of Newton's second law that you're probably most familiar with is force equals mass times acceleration, F equals ma. Force is also equal to the negative derivative of the potential energy with respect to position, so we can swap that out. As we saw before, momentum is just mass times velocity, and unless the particle is losing weight from running around so much, the time derivative of this will just be mass times the derivative of velocity, which is acceleration. Once again, removing the averages, we get F equals ma. Astute viewers may notice that if this were the exact second law, the right side of the equation would be the spatial derivative of the negative of the potential energy as a function of the average value of position, not the average value of the negative of the spatial derivative of the potential energy as a function of position. This might look like a bunch of whatever, but it actually has some important consequences. If the potential energy is constant, linear, or quadratic, like in a harmonic oscillator, then the average value of the derivative of the potential at the average position will be the same as the average value of the potential's derivative. But if the system has a more complicated potential, then there will be a difference between the two. In fact, if the potential is cubic, the difference between the two will be the difference between the average value of the square of the position and the square of the average value of the position. Looks familiar? This is just the formula for variance, reflecting how the more variance there is in position, the further the Ehrenfest theorem is from the second law. If the wave function's spatial extent is small, then the average values of the observables will look like the measured values, and our system will act more classically. This is a general pattern of quantum systems. Another important mathematical analog relationship is between the quantum commutator and the classical Poisson bracket. Like the commutator, the Poisson bracket helps to describe the development of a system in time, and they are related by a factor of 1 over I h bar. Part 3. 2 physics, 1 world. All this raises the question, if quantum mechanics describes what classical mechanics does, but classical mechanics is a lot simpler, when should we use the latter? Broadly, classical physics is used at macroscopic scales. If mass is large enough, then Hamiltonian takes off its hats and becomes classical, no longer involving quantum operators. But of course, it's not as simple as if it's big, it's classical. Things like a toaster, the sun, and silver can be better understood with quantum mechanics, depending on what exactly you're doing with them. A good benchmark for knowing when to use quantum mechanics is the de Broglie wavelength, which is Planck's constant over the momentum. The larger the wavelength, as compared to the so-called characteristic length of the system, the more quantum properties it has, since a wave function's spatial extent is generally on the order of magnitude of its de Broglie wavelength. So if the mass or velocity, or really both, of the object or particle are large enough, then the wavelength is essentially zero, letting us use classical physics. This is analogous to the idea of the h goes to 0 limit. Relatedly, adding particles to a system has been found to make it approach a classical limit. Part 4. Were it so simple. As you might be thinking, the line between quantum and classical worlds is going to be either blurry or arbitrary. All systems, whether we call them classical or not, are composed of quantum particles. In some cases, this doesn't matter. In some cases, it matters a lot. In others, it's somewhere in the middle. For example, if densities and temperatures are high and low enough, respectively, some degenerate gases follow quantum statistics instead of Boltzmann statistics. This is not a clear switch, and at some point a hybrid model of the two may be most appropriate. But this question goes beyond thinking about where to draw the line. A 2023 paper from Sirgi et al. Discusses quantum classical hybrid systems that involve the interactions of both quantum and classical things. For example, many body problems with light and heavy masses, such as biochemical reactions like the activity of the superoxide dismutase enzyme, which involves classical diffusion and quantum oxidation and reduction of superoxide to form dioxygen or H2O2. Measurement, which often involves quantum subsystems in classical instruments or environments, is a case where these hybrid systems are of critical importance to understand how wave functions can collapse like they do under the Copenhagen interpretation. Sergey and friends generated a couple equations to describe two-part quantum classical hybrid systems with their own Ehrenfest theorem and bracket notation, but there is of course more work to be done in this area. At this point, you could, reasonably, say, if quantum mechanics can recover classical mechanics by the correspondence principle, why don't we just use it for everything? And yes, this is broadly true. Quantum mechanics can do what classical does. It just does it way worse. Could you use quantum mechanics to find how long it'll take for a baseball to hit the ground, or how much force it takes to stretch a spring 3 feet? Sure, I was even going to try that here. But it's overcomplicated and a pain. But there's a more fundamental objection to abandoning classical mechanics altogether. Yes, quantum mechanics can recover classical mechanics, but could it create it? Maybe not. Some argue that classical mechanics is needed to create quantum mechanics, and for that reason, quantum mechanics is not a logically closed theory. This was historically the case, of course, and there are still parts of classical physics that have not yet been incorporated into quantum theories, like gravity. So whether we consider quantum physics as an extension of classical physics, or classical physics as an approximation method for quantum physics, it is clear that the two are deeply interconnected, and that we're better off keeping them both around. For now, at least.